M times V, just a little momentum. M times V, just a little momentum. M times V, just a little momentum. M times V. So there you go. That's momentum, and it's your favorite, right? Because it's got a song. But this is angular momentum. It's an L. Yeah, I guess for the same reason as P is linear momentum. Okay, I'm going to try to figure out what angular momentum could be, and I guess it's going to depend on the angular analog to mass, which is, well, let's see, this is linear mass. I guess rotational mass is that thing called moment of inertia, and the angular analog to velocity is omega. Angular velocity. Okay, so we've defined angular momentum, and that's what it is. And look at these units. It's got units of, let's see, the units of L are, the units of the moment of inertia. That's mass times distance square, right? So we've got kilogram meters square, and then we're dividing by seconds. Kilogram meters square per second. Interesting. And the units of linear momentum, the units of P, are just kilogram meters per second. Kilogram meters square per second versus kilogram meters per second. Okay, all right, that's fine. Now, I want to look a little bit more about this L. Let's see what we've got for L. Since L is I times omega, we know that for something that's moving in a circle over here, something that's moving in a circle and attached, that circle is attached, the thing, what do we want? Yeah, a severed hand, actually. Here we go. Let's put this severed hand over here. And it's dried up a little bit too. That's kind of gross. But it is tied to a string, and somebody's swinging it around with a nice live hand over here. And it's going around in a circle. So we could define this distance to be ara, and we've got some velocity there, v. What do you want to say, this direction? Yeah, we'll say it's going in a positive direction. That's tangential speed, that direction, and it's got some mass. The severed hand has mass m. So I want to think about what the angular momentum of this thing might be. So we could look at its moment of inertia, and so because, because it is just a mass at a distance r away from the middle, the moment of inertia will simply be m times that r square, and then we have to multiply it by the angular momentum of this sucker. Sorry, not the angular velocity of it, which is just v divided by r. V over r, because v is omega times r. So we can solve this for omega and plug it in right there. And then if we expand this a little bit, check this out. This is m times v times r. And if I underline in blue, maybe you can tell me what to do. If I underline in blue, I find that L is P times ara. Interesting. I'm not going to write any vector symbols on this because it is just a scalar equation. But just like all the other equations, we find that we can get some angular stuff from some linear stuff by simply multiplying by r. Let me remind you of a few of those. We get, let's see, v is omega times r. Oh man, that's getting something linear out of something. Oh man, that's a little bit different. What we're doing, this is a little bit different. We're taking the regular momentum and multiplying it by r to get the angular momentum. Okay, that is what it is because we've just derived it right there. Now, in general, we might not have something going around in a pleasant little circle like that. So I can draw you another circle and define this angle. I think I'll call it theta. So if I define this to be ara, just as before, I might have a velocity that's not in a circle here. So my velocity could be this direction. That might be the direction of my velocity. I can't even call it tangential velocity. But check this out. There's an angle between r and v, and that angle is theta. And we could also bring this back and make another little triangle here. This is what I would call r perp. R perp right there is the normal distance away, see this right angle right here? It's the normal distance away from the speed. Very much like the arguments that we made for torque. So if we were trying to define angular momentum for this situation, now let me back up here. I really don't like a capital L. I'm going to make it stylish. There we go. Yeah, okay, script capital L. Here's my angular momentum for this. So the battery just died. I want to review the things that I said. I don't think I did anything really earth-shattering, but I want to make sure that you see what I'm doing here. I need to find the angle between ara and the momentum vector. And the momentum vector is obviously parallel to the velocity vector because it's just a difference of multiplying by mass. So then once we establish that there's this angle between it, and the cross product uses the sine of that angle. What this means is that if you're going this direction, and the axis of rotation is right here, and you're going straight towards it or straight away from it, then you'll have no angular momentum. However, if you're going, the axis of rotation is here, and you're going that way by it, then you will have some angular momentum. You're a distance ara away from the axis of rotation with your velocity, then you'll get some angular momentum. This is very similar to torque in its structure. I was just doing a little bit more with angular momentum down here. I said angular momentum is the normal distance away from the velocity. So we can say this velocity, if this thing is moving past the axis of rotation at some weird angle, we can just grab the velocity and bring it down here and say if the velocity were at its closest approach to the axis of rotation, that distance away would be r perp. And so I was just going to say that this is r perp times, we can go in red. Yeah, why not stick with red? This is r perp times m times v. Then you don't have to worry about any signs if you put r perp in there. All right, so I wanted to do a couple questions for you, and those are these. Here is my first question. If my axis of rotation is here, and let's pretend I'm on a table or something. I have a block of wood, and I fire a bullet at it. The bullet is going this direction. Will the bullet cause the block of wood, I'm holding this down, remember? Will the bullet cause the block of wood to rotate in a clockwise fashion or a counterclockwise fashion? So is the torque on the system when the bullet crashes into the block of wood, will it be a positive torque or a negative torque? And I think you'll agree that over here, the torque from the crash will be greater than 0 because it will do a counterclockwise rotation. Now that also means that this bullet, bullet has, let's see, what is this thing? This capital L business right here. The angular momentum is greater than 0 before the crash because it's moving on this side of it. But if I had another bullet over here, we'll do this guy in brown. If I had another bullet over here and there's a smaller rope, another bullet over here with the same speed, you would agree, if this is still my axis of rotation, this block of wood, interesting, would get hit. So the torque of the crash, when it gets hit, is going to cause a clockwise rotation of this block of wood. So the torque of the crash is less than 0, and you'd have to admit that this bullet, sorry about my spelling, wow, focus. This bullet has angular momentum less than 0. So it has something to do with its location relative to the center of rotation, the axis of rotation. This one right here has a positive angular momentum, and in fact, regardless of where it is on its path, as it's going this way, it's going to be up here in a little bit. Regardless of where it is in its path, it will always have the same angular momentum. I guess angular momentum will be conserved. We'll see that in the next video. But angular momentum is the same regardless of where it is on this path because r perp is this distance right here. And on this problem, r perp is that distance right there because that's the closest approach that the bullet ever gets to the axis of rotation. So the angular momentum of the bullet as it goes in the straight line is unchanged. Good. Good. Now, here's the final question. if I have a nasty brown apple, and the apple is moving, it has mass, let's see, mass is, I don't know, 0.15 kilograms, and it's moving at, let's speed things up a little bit, 220 meters per second. What is its angular momentum? Can you do it? Let's see, for angular momentum, we need this equation. For angular momentum, we need r perp times m times v. So there's something missing, r perp. Notice that angular momentum cannot be defined unless we have an axis of rotation. So I could put my axis of rotation over here. Let's do that in pink. And I'm just going to write L for here. The angular momentum, if the axis is here, is what I mean. The angular momentum, if the axis is here, depends on this distance, where I'm going to call that r perp. That would be r perp times m times v. What about if the axis of rotation were over here? What if it were right there? Ooh, what if it were right here? Let's call this location A and this location B. How does the angular momentum of the apple compare if we let the axis of rotation be here or here? Check it out. This is the relevant distance, r perp A, and this is the relevant distance, r perp B. Notice, because we're talking about the normal distance away from the path of the apple is going like this. We are only concerned about the normal distance, so points A and B are the same. We could say the angular momentum at A is, sorry, what I mean to say is the angular momentum of the apple, if the axis is at A, would be the same as the angular momentum of the apple if the axis is at B. And that's just going to be r perp comma A times m times v. I hope angular momentum is starting to make sense to you. We'll talk about it more in class. Circle over here. Something that's moving in a circle and attached, that circle is attached, the thing, what do we want? Yeah, a severed hand, actually. Here we go. Let's put this severed hand over here. And it's dried up a little bit too. That's kind of gross. But it is tied to a string, and somebody's swinging. I'm going to try to figure out what angular momentum could be. And I guess it's going to depend on the angular analog to mass, which is, well, let's see. This is linear mass. I guess rotational mass is that thing called moment of inertia. And the angular analog to velocity is omega. Angular velocity. Okay, so we've defined angular momentum, and that's what it is. And look at these units. It's got units of, let's see, the units of L are, the units of the moment of inertia. That's mass times distance square, right? So we've got kilogram meters square, and then we're dividing by seconds. Kilogram meters square per second. Interesting. And the units of linear momentum, the units of P, are just kilogram meters per second. Kilogram meters square per second versus kilogram meters per second. Okay, all right, that's fine. Now, I want to look a little bit more about this L. Let's see what we've got for L. Since L is I times omega, we know that for something that's moving in a m times v, just a little momentum. M times v, just a little momentum. M times v, just a little momentum. M times v. So there you go. That's momentum. And it's your favorite, right? Because it's got a song. But this is angular momentum. It's an L. Yeah, I guess for the same reason as P is linear momentum. Okay.